Okay, welcome back. When we left off last time, I had asked you to answer these questions on your own. What must happen in order for work to be done? A force must make an object move in the direction of the applied force. So as we said in science and engineering, work has a very specific meaning. And this directly relates to the equation for work, which is work equals force times distance. So if the distance, when you make the object move, if the distance is zero, no matter how much force you're exerting, it doesn't matter because zero times whatever force you're using is going to equal zero amount of work. What's the equation for power? Power is the rate at which we get work done. So it's work divided by time equals power. We said that work and power, or work and energy, were related. So power also equals energy divided by time. And we said that work is the transfer of energy. So it makes sense that the two are related. How is the scientific definition of work different from the common one? Well, in everyday speech, when we talk about work, we often refer to the amount of effort we put into something. So I might say, I worked really hard on this PowerPoint and these notes. But in scientific terms, did I really do very much work? Well, I pushed on the keys of the keyboard, and that was a very small force. It made the keyboards move, but that was a very small distance. So you had eeny beeny forces with teeny tiny amount of movement. So really, practically not much work was done in science and engineering terms. Okay, so I did practically nothing. You might say the same thing about your schoolwork. You might say, I worked really hard on this schoolwork. But in terms of applying forces to make things move, you really don't do that much work. Okay, so now we're going to talk about how people get work done, and we're moving into using machines to apply forces that make things move at distance. So they're directly related because machines help us get work done. So that's the basic definition of a machine. A machine is a device that makes doing work easier. Now, a lot of times kids get confused here because they think that it makes some of the work go away. But if we think about applying a force to get something to move, there is not less work. We still have to move the same object, the same distance as what we wanted to, but machines allow us to do that easier. Okay? So the first thing is we need to understand that machines help move things that resist being moved because they have inertia. Remember, we said inertia was the resistance of an object to changing its motion. So if it's at rest, it wants to stay at rest because of its inertia. There are three ways that machines can make work easier. The first one is they can multiply our force. And we're going to find out that getting our force to multiply comes with a trade-off of having to do the work over a longer distance. They can also change the direction of the force. So like when we use a pulley at the top of the flagpole, we pull down and the flag goes up. So it's not multiplying our force in that case, but it's changing the direction of the force, which is handy because we'd rather stand on the ground and be able to pull down and have the flag go up than have to apply the force upwards, which would be also the direction of the movement of the flag, which means we'd have to, climb up the flagpole every morning to the top to apply the force in the same direction. So having it change direction is incredibly valuable. And then the third way, which is the least common one, at least for simple machines, is it increases the distance over which the work is done. And we're going to find out that sometimes, like with a rake or a shovel or a broom, you just want to be able to apply the force up here and have it come out down there. When we talk about machines multiplying our force, there's a trade-off. The same amount of work can be done by applying a small force over a big distance is done by applying a large force over a small one, since work equals force times distance. So we're going to find out that the machine does this. It applies a small force over a long distance. And this is what we input. So the machine allows us to put in a small force over a long distance, and then the machine puts out a large force over a small one. So there's a trade-off. Okay, so work equals force times distance. This means you can decrease the force by using more distance. This means you can use less force, which is how it makes the work easier, because it allows us to use less force and move things that we normally wouldn't be able to move. Okay? You get to use less force, but you have to go a greater distance, so there's a trade-off. You don't get anything for free. This makes work easier to do, since many times enough force cannot be applied to do the work. So, and one of the easiest examples is, maybe in caveman times, if somebody wanted to move a rock and it was too heavy to pick up, they could jam a stick underneath it and use it like a lever, like a pry bar, and then be able to move the boulder, which they wouldn't normally be able to pick up. But they might only pick up the boulder a couple of inches and roll it, okay? And they had to push down on the lever a big distance, maybe 5 or 6 feet, in order to pick it up just a couple of inches. Okay? By increase the distance by using a machine, you get to use less force. The machine then multiplies our force. Now I'm going to have us look at a simple example with inclined plane. So we have this person over here. They have this 100 Newton box, and the work they're going to get done is 100 joules of work. Okay, so she needs to lift this box up 1 meter and set it on this table. That's what's going to be accomplished. Okay, in either case, it's the 1 Newton times the 1 meter that the box got lifted. Okay, so that's going to be the result. That's the output. So the result without the machine is the force, the weight of the box, 100 newtons, is lifted a distance 1 meter. So the amount of work that gets done is 1 meter times 100 newtons, 100 joules of work gets done. Now, if she made a ramp that was 2 meters long, okay, she would have to push twice the distance. She'd have to push 2 meters, okay, up this ramp, but she would be able to use less force. She would only have to push with 50 newtons. Okay, so we have the distance of 2 meters times the 50 newtons of force, and she still gets the 100 joules of work done. Now, let's say she made the ramp 4 meters long. So now she's got to push the box 4 times as far as what it's actually going to get lifted, this 1 meter. But now she only has to use 25 newtons worth of force when she pushes it up this ramp. Okay? But the same work is getting done. The 100 Newton box is being lifted 1 meter. So we have 4 meters times 25 newtons is the output work of 100 joules. Now, let's suppose she used a really, really, really long ramp that was 10 meters long. Okay, she would only need to push with a force of 10 newtons. Okay, 1/10 of what the box weighs. Okay, but look at how far she's got to push it. Now she's got to push it 10 meters. Okay, and it's only going to get lifted 1 meter. Okay, the thing is she can push with only a force of 10 newtons. So 10 times the distance, she gets to use 1/10 the force. Okay, when it was 4 times the distance, she could use 1/4 the force. When it was 2 times the distance, she could use 1/2 the force because it was doubling what she did. So the trade-off is every time she uses less force, she has to push the box over a longer and longer distance. Now, we're also assuming that there's no friction between the box and the ramp, and she's not losing any of the work due to friction. Okay, now we're going to take this and we're going to go even a little farther. Suppose that she made the ramp 25 meters long. Okay, so it was even longer than what I could fit into this picture. Now she would only have to push with a force of 4 newtons. Okay, so we have 25 times the lifting distance. We could use 1/25 of the force. The machine is multiplying our force by 25. So you see that there's a relationship between here. When this was 4 times, we got to use a 4th because it multiplied our force by 4. When it was 10 times as long, we could use 1/10 the force because it was going to multiply what we did by 10 times. So its distance is directly related to how many times the force is going to get multiplied. And it is because of this equation, force times distance equals the amount of work done. And then as she made the ramp ridiculously long, 100 meters, so like as long as a football field, she would only need to push with a force of 1 newton to lift this box 100 this 100 Newton box, okay, she'd only need to push up the ramp with a force of 1 Newton. But the trade-off is she would have to push a whole football field long to get this box only lifted, about 3 feet up off the ground. So she'd have to push like 300 feet. Okay, but she could use 1/100th of the force because she would be pushing 100 times the distance. Okay, so it's going to multiply her force, and she only needs to push with a tiny force of 1 Newton, and she gets to pick up a 100 Newton box. But the thing is, now she's got to push for a really long distance. But if you were Egyptians building a pyramid, and these were heavy, heavy stone blocks, okay, and there was no way that anybody could possibly lift them, pushing them up ramps, even a long distance, makes sense because you can push with less force and still get it up to where you need to get it. Okay, now there's some basic terms and some vocabulary that go with this. Parts of machine, okay, there's what comes out, and that's the resistance force or the output force. So this is the force applied by the machine to overcome the resistance. The input force, or the effort force, is the force applied to the machine. So in this case over here, the effort, okay, is what you're pushing the box with. The output is the box that gets lifted. Okay. And the resistance or the load is the object that resists being moved. So in this case, it would be that 100 Newton box. Okay. And the mechanical advantage is the number of times the machine multiplies our force. So we said that's directly related to the distance. So you have to go greater distance using the machine to get to use less force. The machine then multiplies your force through mechanical advantage. And the mechanical advantage equals the output force divided by the input force. So when she could push that box for 100 meters and she only needed to use 1 Newton, okay, output was what was getting lifted, the 100 Newton box. The input was the 1 Newton. So it was multiplying her force by 100 times, but she had to push it 100 times as far. Okay, now that ramp with no friction is what we call an ideal machine. It's a machine where there's no friction and the input work equals the output work. Okay, and this is what we'll usually calculate in class. Okay? It's impossible because there's always friction in any actual machine we build. That means some of the work or energy is always lost from what you put in to what you get out due to friction. And the friction changes the energy. It's not actually lost. It's converted to heat and it's converted to wear. So as they rub together, remember we said there's those micro welds. They're rubbing down. You get heat and wear as a result of friction. Now on this page, we're going to take a look at how this works with a lever. Okay, so we have this 10 Newton box. This is going to be our output, and we're going to lift it 1 meter. That's the amount of work that's going to be done. So the resistance or the load is this 10 Newton box. Okay, the resistance force or the output force is going to be the 10 Newtons. Okay, and our output work is going to be lifting it 1 meter. So what's going to get done, our output, is we're going to lift a 10 Newton box, a distance of 1 meter. So we're going to put that in the triangle for work. And our output is going to be 10 Newtons times 1 meter, or 10 joules of work. That's what's going to get done. No matter whether we use the lever or we don't use the lever, what we're going to accomplish is this 10 joules of work, lifting this 10 Newton box 1 meter. Okay, so the work will get done no matter how the box is lifted. You know, part of a lever, and we haven't really talked about this yet, but this part where it pivots on is called the fulcrum. Now suppose we apply our effort force over here so that we have to push down 2 meters. The box is only going to go up 1 meter, and we have to push down 2 meters. So we're pushing down twice as far as what we're lifting the box. Okay, so our distance is 2 meters. The work that's going to get done is the machine is going to lift this 10 Newton box 1 meter. So the work that's going to be accomplished by us pushing here is 10 joules of work, but we're pushing down twice as far as what we're lifting the box. So let's find out how much force we would need. When we put the 10 joules in the work triangle, we have to push down a distance of 2 meters. So when they're up and down in the triangle, we take the 10 joules divided by the 2 meters, and we end up with 5 newtons of force. Okay, so we only have to push down with 5 newtons, and we're able to lift something that's twice as heavy. Now, let's say I put in the effort force way back here, and I have to push down 5 meters. I have to push down, so almost 15 feet, and I'm going to lift this box about 3 feet. Okay, so I got to push down a long ways, and it's going to lift this box a short ways. So I'm trading off the distance. I push a long distance, and this thing is going to lift a short distance. Okay, well, let's find out how much force I have to use. What the lever is going to do is this 10 joules of work. It's going to lift this 10 Newton box 1 meter. Okay, this is what it's accomplished. Okay. My distance is now 5 meters. So I'm going to put 10 joules in the work triangle. My new distance of 5 meters, 10 joules divided by 5 meters means the force is going to be only 2 newtons. Okay, so applying 2 newtons of force, I can lift something that weighs 5 times as much, but I have to push 5 times the distance. So in the first case, the mechanical advantage, what I get done is lifting 10 newtons, and I get that done by putting in only 5 newtons of force. So 10 the newtons cancel, 10 divided by 5, the mechanical advantage is 2. Now in this case, what I get done, mechanical advantage is the output or the resistance force. So my output is I'm going to lift this 10 Newton box. Okay. And also I wanted to point out here that we went 2 meters, we doubled the distance, and the amount of times the distance is increased is also equal to the mechanical advantage. So double the distance, it multiplies your force by 2, which means you can use half as much force. Okay, so I get out 10 newtons of force. I only have to put in 2 newtons of force. That means the machine is going to multiply what I put in by 5. I put in 2 newtons and I lift something that weighs 10 newtons. So if you want to think of it in pounds, okay, this weighs 10 pounds and I only have to push down with a force of 2 pounds and I can lift something that weighs 5 times as much. Okay, but I'm pushing 5 times as far because it's only going up 1 meter and I'm pushing down 5 meters. Okay, so 5 times the distance means the machine is multiplying my force by 5. So there's a direct relationship between the number of times you increase the distance and the number of times the machine multiplies your force. It's actually a direct relationship. You know, we're going to stop here and you're going to answer these questions and then we're going to pick up here next time.